In Chapter 4, when we're looking at reactions in aqueous solutions, a very important first step is to ask what's in the beaker. When we add something like a salt, what happens? Does it stay together as an ionic compound or does it dissociate? In that example, we would be talking about an ionic compound as a strong electrolyte that dissociates to give us ions in solution. Moving on within Chapter 4, we'll now consider what's in the beaker, but begin to discuss it quantitatively. So in today's class, we're going to be looking at concentration of solutions and dilutions. Both of these pair what's in the beaker with some calculations. The concentration of a solution, that's an important idea for us. The concentration is describing the amount of solute that we have dissolved within a given quantity of solvent or quantity of solution. Solute is what we are adding, so maybe that's sodium chloride. And the solvent is the other substance there that's present in the larger proportion. So all the stuff that we're looking at in Chapter 4, the solvent is water, and we're thinking about adding different solutes to it. So the concentration then is describing how much solute we have relative to perhaps the amount of solvent or the overall quantity of solution. There are different ways that we can express the concentration. This semester, we're going to be using units of molarity. That's the moles of solute divided by the total volume of the solution in liters. So if you were to make a solution and you wanted to know the molarity, you could weigh out initially the mass of the solute, put it into a container like a volumetric flask. A volumetric flask is a precise piece of glassware. It has just one line on it. In this case, when you fill it up, it would tell you that the overall solution was 250 milliliters. So you would add water, the solute would dissolve, and it would reach that particular line. In this case, notice you don't know how much water you've added, but you do know the overall volume of the solution. It was the 250 milliliters, and that could be used to determine the molarity. The symbol capital M is for molarity. In this scenario right here, a 1 molar solution of copper sulfate was made. And as I think about what's in the beaker, copper sulfate, ionic compound, strong electrolyte, would dissociate to give me copper ions and sulfate ions. So I could describe that solution as being 1 molar in terms of the copper sulfate, but I'm also thinking it would be 1 molar in terms of the copper ions and 1 molar in terms of the sulfate as I think about how it's dissociated. So molarity, number of moles of solute divided by the total volume of the solution in liters. Solution information includes molarity and volume, and we can use that to calculate the number of moles. If molarity is moles per liter, I can take moles per liter times the volume in liter to get to the number of moles. Solution information of concentration involving molarity and volume in liters is being combined to give me the number of moles. This is going to be really important when we do calculations involving solution stoichiometry, and that's at the end of Chapter 4. Let's work through a couple of sample exercises. They look at these calculations in different ways. So the first one, calculate the molarity of a solution made by dissolving 23.4 grams of sodium sulfate in enough water to form 125 milliliters of solution. So I'm thinking molarity is moles per liter, and I can use a periodic table to get the molar mass for sodium sulfate. It's 142.04 grams per mole. So in this case, let's figure out how many moles we have. We have 23.4 grams. That turns out, if we use the molar mass, to be about 0.16 moles of the sodium sulfate. If we were to put that into a 125 milliliter volumetric flask, add enough water to create the solution, fill it up to the line, 125 milliliters of solution is 0.125 liters. So this is what I would use to calculate the molarity. One thing as a common skill, this conversion between milliliters and liters, we're going to see that quite often in Chapter 4. Now, if I think about that solution, I could describe the solution as being 1.32 molar sodium sulfate. As that dissociates, it gives me 2 sodiums for every 1 sulfate. So for that very same solution, if you ask me what would be the concentration of sodium ions, it would be 2.64 molar in terms of the sodium ions, because I see 2 sodium for every 1 sodium sulfate. That question topic is probed here. What's the molar concentration of each ion present if you have 0.025 molar aqueous calcium nitrate? So I see calcium nitrate. I'm thinking ionic compound, strong electrolyte. It'll dissociate to give me calcium ions and nitrate. 2 nitrate for every 1 calcium. So if the solution was initially 0.025 molar calcium nitrate, I could also describe it as being 0.025 molar calcium ions and double that, 0.050 molar nitrate. Interconverting here between molarity, moles, and volume, this is going to be really important when we do solution stoichiometry. And this practice exercise looks at it. So for the first part, how many grams of sodium sulfate are there in 15 milliliters of a half molar sodium sulfate solution? I'm thinking back to this equation. Moles per liter times number of liters gets me the number of moles. By combining concentration with volume, it gets me number of moles. So for that first part right there, I see that the concentration is given. It's 0.50 molarity. The volume is given as 15 milliliters, so I'm going to convert that to how many liters I have. I divide it by 1,000. That will tell me how many moles I then have of sodium sulfate. Then I could just use the molar mass. I have a certain number of moles of the sodium sulfate. I look to the periodic table and find what its molecular weight is, and this would tell me how many grams that is. The key step within this one is that first part right here. Applying this formula, that concentration times volume gets you the number of moles. Part B is another application of that. If we look within this one, what parts do we have? Well, we see that we have a 0.50 molar solution. We don't know how many milliliters are needed, but we know how many moles we want to obtain. So we've got 2 out of 3 variables. We've got the concentration, we've got the desired number of moles, but we don't have the volume. If we got 2 out of 3, we can solve for the last one. So in this case, you would need 76 milliliters of the 0.50 molar sodium sulfate in order to produce this many moles of the salt. Another topic for us here are dilutions. This is sample exercise 4.14. How many milliliters of 3 molar sulfuric acid are needed to make 450 milliliters of 0.10 molar sulfuric acid? Notice the concentration is changing there. We have initially a 3 molar solution, and we're looking to make a 0.1 molar solution. This is a dilution. We're reducing the concentration. A formula appropriate for that is listed here. M1V1 equals M2V2. M is our concentration, and V is the volume. So we have an initial set of conditions in terms of molarity and volume, and a second set of conditions in terms of molarity and volume. As listed right here, we have 3 out of 4 of those terms. We have initially a 3 molar solution. We want to produce a 0.10 molar solution and 450 mils of it. How many milliliters of that first solution would we have to use? That's what the V1 term is. It tells us we would need 15 milliliters of that first solution. So the procedure would be, we would use something like a pipette where we could precisely transfer 15 milliliters, put it into a volumetric flask. The volumetric flask would be a 450 milliliter volumetric flask. Having transferred in the initial solution, we'd add water to fill it up to the line, and that would produce the new final concentration that we're looking for. This equation, M1V1 equals M2V2, soon as I see a scenario involving a dilution, that's when I want to use it. In today's class, we're going to explore this phenomena of solutions, different concentrations, looking at dilutions. We're going to do that with a computer simulation. The computer simulation will allow you to explore and change some variables, and it will be paired with calculations along the way.